So let's jump into the program because it's not going to be only a demo, but you are going to do the demo. So I'm going to share all the logins for a tool of us, and you are going to log in and you are going to do some graph analytics. But of course we have to do some preparation, so I want to tell a couple of things before we log in and we start the investigation in a network, in a social network. So let's do that. I wanted to be funny and had an idea to warm up, but I think you already warm enough. But still, let's try to first use our brain for a brain teaser. I used to ask this question from the interviewees who are wishing to join to Lynx or to my previous company, and yeah, most of the people can tell it, but it takes quite a lot of time to answer this question right. So do you think you can answer this question fast? So yeah, space diagonals are those diagonals which are going in the body of this hadron, of this dodecahedron. And I help you, the name of dodecahedron comes from dodeca, which means 12. So it has 12 regular pentagons which build its spheres, its sheets. You can use your fingers, paper. Sometimes I allow people to use paper.
Along the surface is not counted, right?
Yes, so if it's on the surface like this one, actually I have a beautiful pen, so I'm going to help in the visualization. So this doesn't count.
Does not?
It's not, because it's not a space diagonal.
Okay.
But this one starting from here and arriving like, ooh, what a diagonal, I was right. Ugh, beautiful. So that counts, like we can start 1, 2, 3, and then I lost. So it will not work like that. Sorry, I'm moving.
100?
Correct. You're hired. Thank you. So the way how I would calculate the 100, I would use graph theory. And the way how I would try to solve it is that, okay, so these are these pentagons. Pentagons have 5 vertices. We have 12 pentagons, so if these 12 pentagons would be not connected on their vertices, then we would have 5 times 12, 60 vertices. But every 3 spheres are meeting at one point, so I have to divide it by 20. So altogether I have 20 vertices, 20 nodes. This object has 20 nodes, 20 vertices. And then I would use my graph theory experience that I know that what I can do is I can connect all the vertices with all other vertices. So I'm going to get all the diagonals, all the edges, all the sphere diagonals and the space diagonals. And then the only thing I have to take out is the edges and the sphere diagonals, and I'm going to get what remains is going to be the space diagonals. So I have 20. I know that from graph theory that 20 nodes, 20 vertices with each other can be connected by n times n minus 1 divided by 2, because every vertex can be connected with another one. But yeah, but we don't calculate 2 times the directions, so it would be 190 total connections between all these points. And then how many edges do we have? It's very easy to calculate. Again, we have 12 spheres. We have like pentagons, so 5, 5, 12. But every two sphere is meeting at the same edge. So I have to divide 60 by 3, right? 60 by 2, so it's 30. So the edges are 30. 190 minus 30 is 160. And the pentagon has 1, 2, 3, 4, 5, or I can calculate also with the n times m minus 1 divided by 2 equation, the body diagonals of this one. So that would be 5. So 5 times 12 is 60. 160 minus 60 is 100, and we got the right answer. So it's really very, very fast if we use graph theory. But you don't necessarily have to use graph theory to answer this question. And there are lots of problems in the mathematics, lots of problems in business, lots of problems in physics, and mathematics is the language to try to formalize the problems. Graph theory is one kind of language. The language what I was speaking when I was speaking the graph theory language is vertices, edges, full connected or completely connected graph. These were the language what I was using, and this language is coming from this graph theory thing. But you can use other But you can use other languages. You can solve things with other methods. Probably the most popular would be calculus. If you want to solve something with machine learning, the first thing what you have to learn is calculus, and how to do optimization. But graph theory is also very useful. Just we saw that with the help of graph theory, we just solve this problem like that fast. And probably with geometry, complex geometry, or with set theory, to answer this question would be probably a little bit more complicated. Or with algebra would be a little bit more complicated and would take probably a little bit more. By the way, did you use the same idea?
Not quite the same, but
similar.
Similar.
Okay. And then should come a long presentation about graph theory, the history, and what are the definitions, who invented what, how they were using, what kind of different applications we know where graph theory is very useful, but we don't have the time for that. So if you're really interested, I can suggest you an amazingly good book in the network science by Albert László Barabási. By the way, he's also Hungarian, like myself. And there are a couple of other Hungarians in graph theory, and probably this is because of the language. So when I go to a client and I start to tell that, well, I do graph theory, and I do graphs, and I solve problems with the help of graphs, everybody thinks that I'm an expert in Excel, and I can do beautiful charts. And with that beautiful charts, it is possible to solve all the problems in the world. So graphs are synonyms for charts, but it has another meaning. The mathematical graphs means the structure which is built up from nodes and edges. In the Hungarian language, we have two words. And if I say graph, I don't think about chart. Nobody thinks about chart. If I say graph, everybody knows, well, let's say 90%, knows that I'm talking about a mathematical concept which is about graph theory. And if I want to say chart, I'm using a different word. So very early age, Hungarians learn that graphs are not charts. Oh, then what are graphs? And then they start to learn about graphs, and then they become scientists. So I really recommend you this book. It's an amazing book. There are a lot of nice videos and the whole story about how the whole thing has started. Everything which is, maybe I'm going to show you this video. Let's just check the network speed. Okay, so I think we are going to have some small problem with the network. I'm just testing this because we're also going to access our tool through the network. So if you experience slow things that might be because of the network. Let's just stop it. Okay. And let's go back here. So I'm not going to tell you the graph story. I'm not going to tell you all the definitions and everything, but still I will tell a couple of things which is necessary for moving forward for our goals. So what are our goals today? What do we want? What do I want to achieve with you? Well, my main goal, and maybe your goal is the same, my main goal would be to introduce you Lynx, which is a graph analytics tool, which is a big graph analytics tool, which my company was preparing for data scientists and data engineers in order to solve those kind of problems which can be formulated in this graph language. Typically for telecom sector, for mobiles or fixed line or advertising, for banks, for insurance. But you can use the same concept and the same tool for biology, for space research and other problems. So what we wanted to build, what we were achieving with this Lynx guide, is to build something which is super scalable. Because big graphs might be problematic to work with very large graphs. So we built our tool on the top of Hadoop with the help of Apache Spark, and the programming language was Scala. All the algorithms were built in Scala, but you will not see anything or not see too much of those things today. I hope I will not make any mistakes. So you are going to see a nice web UI with which you can access the tool, and we are going to log in to, I think, AWS, and we have about 12 nodes which is going to serve you, and hopefully we are not going to have too much latency on that. I've never tried with so many people the tool in the same time. So that is number one, just to find out how nice is it to work with a graph analytics tool, and how easy and how can we do some researches with the app. So I hope everybody has their laptop. You might also need a mouse. If you have mouse, I would recommend to use it. It's easier with the mouse. And yeah, and internet connection, obviously. So the internet connection was shared earlier. You all have the internet connection, right? Okay. My second goal is
just putting the
yes,
internet details.
put there the password. Okay, so my second objective is to teach you a little bit how nice graphs are, from how many different data sources you can build up graphs. It doesn't necessarily have to be something which is obviously a graph, like LinkedIn, for example. It can be something which is much different than that, and still it might be useful to analyze it as a graph. My third objective is to teach you a couple of descriptive analytics for graphs. So learn that what are the most important properties of a graph, what you should check if you have the time and ability to check those properties. And if you know those properties, you know much more about the problem or the setup of the problem, what you try to solve. And also, this is going to help us to better understand why big graph problems are big data problems. Because when you typically hear about, any questions? Yeah.
Spencer guessed 2018 explanation mark.
I will move back and forth. So because your typical big data problems are, you never hear this graph story, right? You hear natural language processing and image processing and videos and text-to-speech and translation and self-driving cars. This is typically big data problems. Nobody talks about graphs and graph theory. So is it really a big data problem or is it not? I would like to talk a little bit about that. And we are going to do a little bit of predictions with the help of graphs. So I would like to show you that if your problem can be formulated as graphs, then sometimes you can build better predictions than if you don't use this graph setup. And what we are now, what Lynx Analytics is right now researching is like completely changing the way of neural network machine learnings. And our idea is, well, actually it's not our idea, there are a couple of articles in the literature, but it's not very popular yet. So the idea is that we are going to put in every single vertex an independent neural network which is able to learn from the neighbors, from the connections, and from the neighbors, and so on and so on. We are not going to do that today. We don't have an implementation yet in the Lynx guide, but maybe if we meet next year, we would be able to do something like that too. Okay, so still I have to define a little bit what is graph and what is graph theory. So the most important elements of the graphs are the vertices and the edges. Both are sets. The vertex set would be like set of nodes. It can be numbers like V and W, and all these things are going to be called as vertices. And I am going to call it vertices or nodes or just points. These are all synonyms for me. And I have pairs of vertices, which is defining an edge. So VW is an edge if V and W are vertices in the vertex set. And if I list the set of vertices and I list the set of edges, then I got the full graph. I can represent the graph. I have a couple of names. I usually measure how many vertices altogether I have. It should be a finite number, most of the cases. And I'm going to note it with small n. And I need the number of edges. I usually note it with large M. And again, there are different names for it. I'm probably going to forget that I initially wanted to call them rank and size, but we always understand what we are talking about. And there is also one thing, what I'm going to call as degree. So every single point can be calculated how many edges are connected to that point, that vertex. And the average of that number is going to be the degree of the graph. So typically, and I'm going to define it a little bit later, but typically when you see a graph, the average degree is going to be calculated by this formula 2m divided by n, and later on you will realize that I used the same formula when I was solving the dodecahedron problem. It's not always true, but like let's start with that function. Okay, so if a graph is so simple, you don't need anything, just vertices and edges, then why are they interesting? And the reason why they are interesting is because if you tell me these two numbers, n and m, and they are large enough, then I can draw millions or billions or potentially almost infinite number of different topologies with just these two things, the number of the edges and the number of the vertices. For example, let's just have two very simple examples. This graph I would call complete graph or full graph. This was the graph what we used for solving the dodecahedron problem. And of course, if you tell me that a graph is a full graph, there is only one way to be a full graph, right? Again, it's not 100% true. I'm going to define it later on. But if you just take a look, like this is the way to create a complete graph, and then every node is connected with every other node. We can calculate the degree, which is like 1, 2, 3, 4, which makes sense, n minus 1, yeah, basically that's it. But we can also build up a graph like that, which is a star, or I can also call it as a tree, which contains the minimum number of the edges. So with only 4 edges, I was able to completely connect these 5 vertices. So it seems that the minimum edges which is needed is n minus 1. The vertices number minus 1 in order to still have a connected graph. But the thing is that in between these two extreme structures, there are lots of other types, topologies of graphs. And of course, if it's only 5 vertices, then it's not so many. But if it would be 50, it would be a lot, like thousands. And if it would be like 1 million vertices and let's say 10 million edges, then it could be an super high number of which contains all the possible types of topologies connecting these them. And they are structurally different. They would be structurally very, very, very different. And when I'm talking about structurally different, I'm really talking about only the graph sets, like the list of edges and list of vertices. Because how I'm going to, for example, visualize it, for me it doesn't, like for me these two graphs are the same. I have the same vertices, I have the same edges, but I was visualizing the two graphs, the same graph, different ways. The two graphs are, I call it isomorphic, because they look exactly the same if I list the vertex set and if I list the edge set. There would be no difference. And again, I'm cheating a little bit. There are even more isomorphism in graphs, but let's just not go into that very detail. I'm also going to use, I already used a lot of simplifications, because there are many different types of graphs what we can observe. And these are these 5 things which I think is important to tell. So first, what does it mean directed, undirected graph? So if in the edge set, it is important to mention that VW is a different type edge than WV, then it's a directed graph. It goes from V vertex to W edge. But if I'm talking about an undirected graph, by definition, I assume that it doesn't matter. The direction doesn't matter. So if VW is there, then WV is also there. I'm not going to count them separately. Weighted graphs, if the edges can have attributes. It can be a scalar or it can be also a vector attribute at the edges. Oh yeah, I have to mention. So Lynx Kite, our tool, what you are going to use, cannot treat undirected graphs. For Lynx Kite, every graph is a directed graph. And it can cause sometimes small difficulties, but don't worry about that now. Weighted, Lynx Kite can easily handle weighted graphs, so attributes on the edges. For example, just think about a telephone network. I call someone, so that is an edge in between us, and the duration of the call could be the weight of the edge. We call a graph simple if there are no loops, so I'm not calling myself, and there are no multiple edges. Multiple edges, if I call my wife 3 times, then that would be 3 edge. But when a graph is simple, I just merge these 3 overlapping edges, parallel edges, and I say that there is just 1 edge in between us. But of course, I can weight it, and I can say that the weight of this edge is 3 because we called each other 3 times. Typically, we are analyzing sparse graphs, and that is going to be the real interesting problem here. So a graph is sparse when the number of the edges in the graphs are much, much, much less than the number of the potential total number of the edges. And of course, when I mention the potential number of edges, then I usually think about undirected simple graph, because if the graph is not simple, when there can be multiple edges between 2 vertices, then basically there is no upper limit for the edge, and again when I say here the maximum edge, only if our graph is undirected and simple. So the spare property is usually connected with the undirected and simple graphs. And there is one more thing what we have to learn. This is the connectedness of the graph. So I call a graph connected if any vertex can be reached with any other random vertices. So this is a connected graph, and when I say minimum edges, then of course only if we are talking about connected graphs, because if I can talk about not connected graphs, then I can easily say that, oh, there is no connection between 3 and 1, and then poor 3 is going to be one component, and 1, 2, 4, 5 is going to be another component. This components thing, number of components or the connectedness, is one thing that a lot of scientists are researching, and it is a very interesting question. What is the phase transition when a graph is going to switch from non-connected to connected one? And of course, we might think that if a graph is sparse, then it is not going to be connected. But also, if we think a little bit again with this example here, that the minimum number of edges which is enough is n minus 1. So this is linear in n. This one is quadratic in n. For a very large n, the difference between the two things are going to be huge. And for assuring that the graph is going to be connected because you build up a tree or you build up a star, n minus 1 is enough. But of course, it's a very special topology. A tree or a star is a very, very, very special topology. So we know a lot of things about the graph. Other KPIs what we are going to use today is degree or scale distribution. So this is nothing else. Just I told you what is a degree. Every vertex can count how many edges they have. So I can build a distribution on that, like calculating that how many edges have 0 edge, how many vertices have 1 edge, how many vertices have 2, and so on and so on. And I can build a beautiful histogram and distribution on that. So that distribution is super exciting, how that looks like. We are going to check it in my example. Diameter and characteristic length, another very interesting thing. Diameter is the longest, shortest path in the graph. So, for example, here, every vertex can be found in just one direction. So the diameter here would be 1. The diameter here, like this is a path. This is from 2 to 4. This is a path. So then here the diameter would be 2. And of course, from 2 to 4 here you can also go in 2 ways through 1. But this is not the shortest path. The shortest would be the direct one. So that is the diameter. And a little bit more complex than the diameter would be the characteristic length. So we calculate all the shortest paths from every vertex to every other vertex, and we just average it. That would be the characteristic length. So, for example, if you meet a if you meet a stranger and you start to talk with him, you will realize that you have a common friend. Then you shout out that, wow, the word is small. Basically, we are talking about that the word has a very small characteristic length because of that. And I don't know if I mentioned here 6th degree of separation, but the 6th degree of separation is the same story, that basically any random people on the world can be reached to any other random people in the world in just 6 handshakes between friends. That is the idea of the 6th degree of separation. You can learn more about that in the book. Connected components, I was already talking about the connectedness, but if the graph is not connected, then basically the diameter and the characteristic length cannot be calculated, right? That would be infinite, because any random vertex from any other random vertex not necessarily can be connected. So in that case, I can calculate these parameters for every separate connected components, every small component of the graph. And the clustering or the concentration coefficient is something about how likely is that my friends are also the friends of each other? Like we usually say that my friends are also my friend. Friends of your friends is also my friend, whatever. So that means that somehow there are these groups, and if there are people who are knowing each other separately, then it's very likely that any random of them selected are also knowing each other. Our world is something like that, like our friends are also usually friends of each other. Our separate friends are also usually friends of each other. Our world is very clustered. It seems that our world is very, very strongly clustered. And there are some evidences of that. Okay, so let me define 3 super exciting type of graphs. And it's worth to define those graphs because I told you that the interesting thing is the topology and the way how I'm going to create graphs with different rules, with different mathematics behind, or with different algorithms behind, is going to create completely different topologies, and these completely different topologies are behaving very differently if we put them into some kind of a business problem or mathematical problem. So the first type of graph what I'm going to define is the lattice graph. We can define n-dimensional lattice graphs. Here on the example, this is a 1-dimensional lattice graph so the dimension is 1, the number of vertices is 8, right? Yes, it's 8, and the k parameter, the degree parameter is 4, because every single vertex is connected with 4 other vertices. It's very regular, it's beautiful. It can be much larger if the n would be not 8 but 16 or 256. The idea was that this chain would be the same. Or if I defined a 2-dimensional graph, a 2-dimensional lattice graph, 2-dimensional lattice graph with 1, 2, 3, 4, the degree of 4 with a lot of vertices, it would be just like a grid. Right? It would look like a grid, a 2-dimensional, beautiful grid. 3-dimensional would be a 3-dimensional thing, cube or something like that. So it's very regular, it's very nice. So because it's very regular and very nice, it is very easy to calculate its parameters. For example, we know that for a 1-dimensional lattice graph, the characteristic length would look like this equation, and the clustering coefficient would like this equation. We have another type of graphs, which are the random graphs. And the random graphs were studied in the 1960s, 1970s very heavily, and a lot of beautiful theorem was found. So the random graph, again, you don't tell anything else, you just tell how many vertex do you want and how many edge do you want. And then the algorithm randomly going to throw out the edges across all these vertices. And the beauty is that if it's real random, then every time it throws out these edges, somehow the topology, somehow the behavior of the graph is going to be same. One beautiful theorem, really nice, you will not find it in the book, for that you will need other books, but what beautiful thing is that it's really shocking that relatively small number of edges are going to be enough to make a random graph connected. Again, we can see that the rank here is linear, is logarithmic scaled. The degree is logarithmic scaled in the order of, in the function of the number of vertices. So for a random graph, we can also very easily calculate these numbers. The characteristic length for a random graph would be logarithm n divided by logarithm k, and the clustering coefficient would be k divided by n. Oh, this is beautiful. So let's have a lot of experiments, and when we do a lot of experiments, we would realize that typically in these very regular lattice graphs, the characteristic lengths are large. Like imagine a huge chain or a huge grid. To take just 2 random guys, the probability that you have to go on many ways is relatively high. The probability that your length, your path length is going to be is quite likely. Our world is not like that. Like our world is a small world. We used to get people close to us, relatively close, in 6 steps. In this one, in this chain, if the chain is really long, you might have to go like, anyway, you see already there are a lot of steps to reach any other random place. But the clustering coefficient is also quite large. And in that sense, the lattice graphs are similar to our world, because we also know our friends are knowing each other. You can see that this is a small cluster here. Almost everyone knows all the friends. So these small communities are appearing. And they don't know those ones who their friends also don't know. So the clusteredness of this very regular graph is high. So on one part it looks like our world, but in other part it doesn't look like our world. For the random graph, for the Erdős-Rényi random graph, the characteristic length is typically very small. If you create a random graph, because of this randomness, any two selected random points are not too far from each other. Because you are going to find some ways to connect. Of course, the graph has to be connected, but we already see that it's almost always connected if k is larger than logarithm n. So in that sense, it looks like that our world is more like a random graph than a lattice graph. But the problem with the random graph is that k minus n, you remember the sparse, we want our graphs to be sparse, so the k compared to n is going to be relatively small, so k divided by n is going to be small. So the problem with the random graph is that if you take a random graph, then if you select one point, their friends are not going to be the friends of the others. The probabilities are diminishing in that sense. And then came with a great idea, these two guys, Watts and Strogatz, and they said that, is it possible to construct a graph which is having the concentration property from the lattice graph and the short characteristic length from the random graph? And what they did was very, I think, straightforward. They took a lattice graph and they started to change the edges randomly. And they set the parameters where they were able to reach out to a graph which was like that. And then they said that this is a small world graph, Watts-Strogatz small world graph, and they said that our world is like that. And every example for graphs, like the calling circles of a network operator, the internet, where the pages are connected to each other with hyperlinks, Facebook or LinkedIn, which is a social network, all these graphs, all these structures, all these topologies are Watts-Strogatz type of small world graphs, because the characteristics length is small, but the clustering coefficient is high. And they did a lot of measures. Do I have that slide? No, I don't have that slide. But in the book, you would find that there are a lot of measures which are showing that this is the situation, that our world and Facebook and the co-authorship graph is having this smaller property. And then came the guy who wrote the book, Barabási Albert, and he said that even there is one more property, the scale freeness of the graph, which is important, and unfortunately the Watts-Strogatz graphs are not scale free, not necessarily scale free. So he used another algorithm, but that's a too long story. I'm not going to go into that. You will, if you want, you can read the book. Okay, so that is enough for theory, and now let's do the practical thing. So I would like all of you to access that site, educate.lynxanalytics.com. I'm really begging that it works. You should get this screen.
Sorry, I can't see a URL.
educate.lynxanalytics.com. Like the name of the tool is Lynxkite, the company name is Lynx Analytics, and the education version for Lynxkite is Educate. Works? Yeah, cool. So I created, let me see. Yeah, I created logins for you, and I have to share those logins with you. So let's see. Let's see if we have that. Okay. So you are going to be A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V. So your login name is going to be student dash caps your number. And because I'm really afraid that if more users going to log in, then it is going to completely crash the system. And I'm not going to tell the password for the live stream, but you can check it from that thing. The first word is there, 4 letters. It should work. Let's go back to the slides. Okay, so what are we going to do? We are going to analyze a social network. We are going to analyze Facebook data. Not a very big one, a relatively small one, but still big enough to understand the main concepts. And the way I was generating this data is I have myself, my Facebook ID, and I have downloaded every other profile who are my friend. And I asked permission for that. And then I also downloaded the edges between them. So if they're friends with each other. We call that type of sampling ego network. This is my ego network. This is my first degree ego network in Facebook. And of course, this means that my degree, like my number of friends, are going to be complete. I have everyone there. But my friends' degree is not going to be complete because they might have other friends who are the friends of them, but not the friends of me. So that is going to be the network what we are going to analyze. And we are having a nice, actually we have a couple of nice questions to be answered. But the first question is that why do I use Facebook? I mean, I really like Facebook for showing the graph problem, but why Facebook is a good example? The first reason is because Facebook is the most beautiful place to learn graph theory. There are lots of vertices, lots of edges, lots of attributes on both of the edges, both on the vertices. So if you work for Facebook and if you are a graph scientist, you are going to do the most beautiful thing what a graph scientist could imagine for him or herself. This is a very good article which is trying to identify the romantic partnership in Facebook just using the topology, just using friends and friends who are connected to each other. And it turns out that with this graph method, with this topology method, it can be identified with a higher likelihood who is your romantic partner than if you do text analysis or image analysis on Facebook, picture analysis on Facebook. But there are a lot of other articles about how different nations are connected to other nations in Facebook, how groups are connected, how communities are formulating, how can we identify fake profiles. So there are lots of interesting articles about graph theory and Facebook. So that's why I think it's a lovely place to learn and to get new algorithms and new ideas from. But the other reason is that I strongly believe that almost every other industry can build up their own social network data. Like think about a telco company, think about Synctel. All your data is there at Synctel. If you call anyone, this data is recorded, they can build up their own graphs. Or think about DBS. DBS measures who or sees what transaction do you do, who do you transact with, who do you have lunch together with, and then you split the bills. they know all of this information, they can also build up their social network. And of course, this social network can be better or worse than Facebook, bigger or smaller than Facebook, depending on how much data you have. But the beauty is, and I just measured it many, many times when I had the chance, is that there is a very beautiful overlap between those things. So if you had, let's imagine if you have Singapore's Facebook as one graph, and you have the calling circle from Singtel, and you just put the two things on the top of each other, you would see that there is a huge overlap between those things, between those structures. So if Facebook is able to find romantic partnership in Facebook data, then quite likely DBS would be also able to find romantic partnership in DBS data. Different likelihood, different probability, different number of training sample, but this is basically the concept. So this is going to be what we are going to do. We have Facebook data, and we have these 6 tasks to do. I think these 6 tasks would take about 12 hours. Do we have time? But I'm not going to take away the login credentials from you. So if you want to continue, or if anyone on the web would like to do something and do some analysis by themselves, I can provide you more access, more time for experimenting. And yeah, basically these are the tasks what we are going to try to do step by step. I think we are going to arrive to the romantic partnership today, and the rest can be homework. But all these things are possible. So it is possible to find homogeneous groups. It's possible to build up models for predicting who speak different languages. It's possible to, because finding my romantic partnership or my father or my sister is relatively easy because I have definitely all of them in the network. But my friends and my friend's wife is not necessarily in the network. And they definitely have much less edges between them than I have with my wife there. So that would be a much more difficult thing, but still that is possible to do with the Ego network. So yeah, all of these things are possible. And I think that's it. So let's go and let's really do the thing. So everybody should be able to go to the Graph meetup, and everybody should be able to access this sheet, this project. Actually, what we have in Lynx, we are having data and we are having projects. So the data I already uploaded, and I created a project where we can check this uploaded data. So who doesn't have this? I know that you don't have, and you are W. You are E. Yeah. Okay. So what you have to do is you go here, and because this you can read, but you cannot write. So you come here, and you say that I want to save it at another folder, and instead of the Graph meetup folder, you have to put into, and I forgot that's great, I forgot the syntax. It's users, and then the thing, okay, users. So you come here and save it to users dash student E, right? Student E, but all others you save it to your own folder. And then you can keep the rest of the name, or you can give a different name, whatever you wish. And just click to yes, and it should be now in your folder. It's not your folder, it's still the trade folder. Anyone else? Go out, yeah. Go to student E. Yes, you have it. Cool, you can access it just with a click. Everyone has it? Cool, okay. So now you can already edit the file, and yeah, I have to go into my folder to be, actually I have to save it to my folder. Okay, I also saved it for myself. Okay, so I was already preparing this data, but if I didn't, I show you how is it possible to, and I'm going to sit down now, to load any other new data sources here. So if you want to load new data, you just access here the import icon, and there are different types of databases what you can import. So most likely, in this case, you would like to import something from your computer, which can be a CSV file. You press, and then immediately this icon appears onto your working folder. And if you double click, I told you if you double click, then a communication bar is going to appear, and you can select here what would you like to upload from your computer. I already uploaded these things, so I'm not going to upload anything now, but later on, if you want to do some experiments in your own folder, you can upload your Facebook data if you have it, or LinkedIn, or any text if you want, basically whatever can be uploaded, and then separate it, so then you have to use those things. And after that, you press the import button and you're done. You imported the data.
One question I have. How did we get that data from Facebook?
So the API is closed. You will be not able to download the data from Facebook anymore. This has been closed a couple of years ago.
Okay.
But you can do it manually. Okay, so yes? You can. You should be able to. And let me check. You should be able to load any data. Because you haven't moved so you're still in the graph meetup. You haven't copied your stream. You will not be able to do anything with that.
Oh, but if I create my own folder.
So you have to put it first into your own folder.
Okay.
So you already put it into your own folder?
No, I haven't created my own folder.
No, your own folder has already been created. So now you have to close it.
Yeah, okay. And then here we are.
Yeah, now you go to the save. And here you have to put their users and then student whatever, I don't know what, and then it is on your own folder.
Because after I log in again, right? Because just now I
You logged yourself out?
No, because just now I cannot, after I import, right?
Yes.
Then it say I do not have the right access. So I log out, then log in again. Now the folder is gone. It's not there.
The folder is there, but the file is not here, right?
Yeah, the group meetup one is not here already.
Okay, so don't log out. Student age. Okay, I'm going to. So once more, if you forgot to save your file in the right folder, then you come here and you put there users, and after users you put your own username. You are student age. Student-age. And it should be there. Okay. Wow, there are a lot of folders created in the meantime. Guys, just follow what I ask. Don't do other things. This is a beta version. If you do other things, you are going to crash the whole thing. Okay. No. Later on, everybody can do some experiments. That's the idea of the training today. If you have an error message, you just click and you can delete the error message, not disturb you. Okay, so let's see what kind of data I have here, what kind of data I have already uploaded. And to take a look, you can just go into this green circle and press, and then it gives you a table, a small table, what you can immediately access. And this is quite straightforward. You can set the limit to 20, and then you got a 20 line. And it is quite nice because I was taking care not to import some garbage. So what you see is a Facebook ID, a first name, gender, a location setting, Facebook rank. Facebook rank has ranked all my friends to order based on when they have joined to Facebook. So one would be, or an early one like 6, Agnes is someone who joined very, very, very early. And others are...
That's your wife.
Maybe. There is a dummy variable for male, there is a dummy variable for Hungarian, there is a bean variable for age, and you can see that all the variables that I have imported are in string format. So Lynx kite is reading all the variables in string format, and then later on you have to convert them to integers or reals if you want to use them as numbers. So this is basically the vertex set. This is the set of vertices, and I can already start to play with that because I promise you that I'm going to show you a lot of different ways how to create graphs. So I can just say that, okay, I want to use this thing and build a graph for me. So what I have is a table, and I want to use it as vertices. So I'm going to select this one, use table as vertices. By the way, if you just lost, then you can put there use table as vertices, and then you are going to find it in the find menu. And I always forget how to close it, like that. And then the thing what you have to do is connect the data with the graph builder, and this is so easy that you just do this. And if you are like a little bit control freak like me, then you can press shift, and then you can order it in nice grids. Then the grid size is going to be equal. Okay, so let's see, what do I have to tell when I want to use table as vertices? Basically, I don't have to say anything. I can give an internal ID name if I don't want to use it as just ID. And that is very necessary because this is the moment when the graph database is created in our system. And it always needs an ID. But for us, it's not going to be important anymore. And now, if you click on the green thing, you don't have anymore the table format, but you have something which is a project. It calls that we already got a project. And in that project, it is very kind. It tells us that we have 403 vertices. That would be the n, if you remember, and no edges, m. There is no wonder we have no edges. And for vertices, we have attributes. We have the age bin, the Facebook ID, the Facebook rank, the first name, the location settings, and so on and so on. And it's so cool that you can just go in and, for example, okay, check what kind of location settings do I have. Yes?
Something about the parameter, source ID column parameter.
So can you just click in? Yeah, so you use table as graph, but I wanted to use table as vertices. Use table as vertex.
Use table as vertices, and user C does not have permission.
Yes, because again, you didn't do what I asked earlier. You're still in the graph meetup folder. This is you don't have write access. You only have access in your folder. So you have to first copy it. Yeah, users, student, have you copied it? No, you didn't. So first you have to copy it. Go back. Yes. Go to graph meetup. Go open it. Go to save. And save it to user and users / your folder. Anyone else need some help? You just connect it. You cannot connect? Why? From here to here.
Oh, just drag.
Just drag. Yep, just drag. Easy, easy peasy. Not like Python. So can you just click in? Yeah, so you use table as a graph. But I wanted to use table as vertices. Table as yes, because again, you didn't do what I asked earlier. You're still in the graph meetup folder. This you don't have write access. You only have access to your folder. So you have to first copy. Users shouldn't have copied it. No, you didn't. First, just yes, we go back. Go to graph meetup. Open it. Save. Say user and users slash. Anyone else with some help?
Use table as vertices. Use table as vertices.
You cannot connect? Easy, it's easy. Not like Python. Okay, so guys, you are still in the graph meetup folder. You don't have to write it, like only read it. That's why you have to copy first to your own folder. So go to save, and here you have users, dash, and your answer for that name. Users. Okay, one more. If you don't have write access, ladies and gentlemen, if you don't have write access, then you are not in the right folder. Here you should have user, dash, student, whatever, and then the name of the file. If you don't have it, you go, click the save button, and save it into your own folder. Please. Good. Now let's see. So we have this beautiful distribution here for the location setting, and you can already see that out of my 403 friends, there are 225 who are Hungarians, actually whose language setting is Hungarian, 137 whose language setting is US, 35 whose language setting is 35, 2 Russian, 2 Croatian, and 2 German ladies. No, don't know they are ladies, but you can find it out. Because we also have here, turn off. Button turn on, yeah. All kind of problems in the same time. It's okay. So we have boys and girls. So for example, if you want to check that those 2 girls are, those 2 German friends are girls or boys, then I just write here filter female. So if I click wherever I want to click, it's going to immediately do the filter. I only have girls now. And then the filter is still active. I go to the location settings, and yeah, I have 2 girls. So they are girls. That's how it works. And if I'm confused a little bit, then I can see the total. I have 403 friends. Out of them, I have 178 females, Then I did the selection, the total is 178. And if I go here, the total is 178 out of the 433. And I just click here into the small visual box, and the two German ladies will appear. Actually, the Croatian friends are also girls, but the Russians, there is one boy, one girl. Because earlier there were two here. To discard the filter, we just delete it and click out. Alright. Okay, so now let's do some funny thing. You all wait for creating a graph, right? We are going to create a graph. You all think that I'm going to load in the edges between my friends, but I'm not going to do that. I'm going to build a graph with a completely different way. I'm going to connect those people who are having the same first name. And then you can ask me later on, why the hell are you doing that? But let's try to do this just for fun. So for doing that, I have to search for the right command. It definitely should be something like connect. Connect vertices on attribute. I think that looks something like good. So let's select the connect vertices on attribute. And so if you want to do now another trick, and if you don't like this way of connecting the building blocks, then you can just bring them close to each other, then use shift, and this is a real control freak version of creating your projects. You double click here, and this is asked that, okay, so what do you want to connect with what? Do you want to connect the HBin as source to Facebook ID? And in that case, if one vertex HBin would match another vertex Facebook ID, then it would connect the two. But of course, this is quite stupid thing, right? It is not going to match. So what I would like to try to match is if the first name is matching the other's first name. And then let's click the blue button. And it is going to count, like I'm trying to connect people. And at the end of the day, it comes out that I have 1,310 edges between my friends. And I think it is the right time to do some visualizations. So you can do visualization from here, but I really like to use the proper visualization button. So I'm going to click here. This is the visualization, the graph visualization. You are going to have this nice eye. And then you click in. That is going to give you one panel. So that was when I clicked the eye. It is going to give me the communication panel. And if I click the green thing, it is going to give me the output panel. And let's try to understand what's happening here. You should get something like that. Maybe not exactly the same thing. This depends on the random generator. Probably the same. Okay, so this is the visualization panel where you can communicate with this visualization thing. Here you can do a lot of settings. So first of all, or for example, you can visualize different attributes on the chart. Now it tells me that they are connected, so they must have the same first name. So I'm going to put there the first name. Yes, both of them are Tamás. Tamás is Thomas in Hungarian. Their settings is, I can put there that, the location setting, I'm going to use it as color. So sorry, maybe I was a bit too fast. So first name, I pressed label. So when I pressed label, it gave me the name labels. Oh, everybody has Tamás or somebody have different? Yeah, you also have Tamás. Good.
So
but
why do we only have two vertices?
I will explain it. I will explain it later. Let's use the other, the location settings with color. And then it is going to show me that, interestingly, although I have two Tamáses here in this chart, but one's language setting is Hungarian, the other's language setting is English. And I think now you are getting closer and trying to get what I'm trying to do. I'm also going to put there the gender, sex, and let's use icon. So the two icons here are boy icons. You can see clearly these two guys are boys. And now a very good question. Why do I see only 2? Because I should see 403. But it's not possible, unfortunately, to visualize 403 vertices. You wouldn't be able to see that. But it's possible to visualize a little bit more. So just if you're done with that, everybody has 2 different colors Tamás on the chart connected. Part, the visual setting part, and you're saying that centers, which is set now to automatic. Instead of auto, you say that pick me 1. Instead of picking 1, pick me 2 guys. Pick. So then it is going to appear one ID and another ID, and the Tamás are remained. But if you have different settings of the image, then you should see Gary as well. Who sees Gary? The way how I'm zooming in and zooming out, that's why I wanted to suggest to use the mouse, is with the help of the middle, what is the name of the scroller thing. If you don't have mouse and you wonder how is it possible to do, I have no idea. Maybe you can search it in this help thing. But I think you ask again the question that you selected 2 and now you see 3. It seems that the computer is doing some completely stupid things, but it's not the case. It is because there is also a radius setting, and the radius was set to 1. So if you set the radius to 2, you are going to see exactly 2 customers. Sorry, if you set the radius to 0, you are going to see exactly 2. If you go here and say that I want 5, say pick, and you keep the radius to 0, then you should see 5. Okay, if it's really annoying to do this thing and you don't have the scroller, then what you can do is you go here to network layout and let's ask centralized layout, and let's press play. Does it work? Now I even make it larger. If you were interested in how I did that, I again used the scroll bar and I was pressing the shift and the scroll bar, and I can make them large or small. And now we understand why do we have exactly 5 vertices, because we set the radius to 0. If we set the radius to 1, then we are going to have 8 vertices. If you keep it on play, then it's still going to nicely move a little bit. And we see that we have 2 Katas and 2 Tamáses and 2 Mártons. And if you go here and pick another 5, then we will see that we have 3 Lacis and 1, 2, 3, 4, 5, 6 Jánosis. These are graphs. These are connected components. These connected components are always complete graphs. This is just because I was generating it like that. It is not possible to have not a complete graph, because if somebody is called the same, and if somebody is called the same with the third person, then all of them should be connected. So it is generating this way of connecting my friends, has generated these name graphs in this topology. And yeah, if you want to play a little bit more, I will leave you a little time to do different visualizations. Even, why don't you try out the 3-dimensional visualization, and why don't you try out the 3-dimensional visualization by visualizing all of my friends. So visualizing all of my friends, I think if you write here star, then you have all. Yeah, correct. And I'm not telling quite the truth, because those who are only having one single unique name, you won't see it in this three-dimensional chart. Okay, I let you play a little bit with visualization, and also I give you some time. If you have questions, you can ask. So the way how I was visualizing all of them, I was putting here a star, or you can also pick a lot of numbers. You just go in, click in, and put in, instead of 5, you can write 50 or 500, and it is going to, then it's going to create all of them. The star you have to put here.
Here.
Yes. Yeah, then it is going to visualize all your edges. So clear those ones, and put instead of, yeah, just put star. And I think the reason why it's not showing is because, okay, so the reason why it's not showing is just close it. And instead of the inbuilt visualization, you should use the visualizer. Yeah. That is a better way of doing visualization, graph visualization. Yeah. If I were you, I would just delete this one, because that's just not necessary, and do the proper visualization. Works? Questions? Anyone wants to ask a questions? Okay.
For some reason, I end up with this.
This is beautiful. I really like it.
Wow.
Awesome.
I don't know how I did it.
You did it. The only thing, you did the same, but instead of visualizing in 3 dimensions, you visualize it in 2 dimensions. So if you want to visualize it in 3 dimensions, you just click here and say that do a 3D. And of course, you get a nicer chart.
I don't know how I did it.
This was good. You just click the 2D. It's okay. Beautiful.
I look at everything. I don't know how I did it.
Of course, the idea here of this training is that you would know how you do it, how you did it. But of course, yes.
Well, somehow it stopped running. I think it crashed, or is it still trying to run?
It's trying to run, but if I were you, I would
Just delete.
yeah, just get out from here and try to get in once more.
So I delete this guy, maybe. And
Maybe you delete. Is it working like here? You have something, yeah. Okay, so just delete the visualizer and try to run another one. Because the thing is that the visualizer is using your own resources,
right.
so that that can crash because this is an
Okay.
Apple. Okay, shall we continue? So the thing what I want to suggest here is that we never thought that with a simple flat file, having just names in it, we are already able to create a graph. And of course you question that why is this good? I can give you an answer. For example, because earlier we saw that, oh, and I'm going to do the same thing. So because, for example, we can know that if we have 1, 2, 3, 4 Kristas who are Hungarians, whose language setting is Hungarian, then the 5th one whose language setting is Great Britain, it probably also speaks Hungarian. The name is the same. This Krista, well, it can be a British name, but then not with SZ, which would be a typical Hungarian character, SZ. Same with István's. And of course, there are other names where you cannot be sure in that, like for example, Robert. Right? Robert would be the same spelling in different languages. So if I want to build a model who speaks Hungarian, this type of representation of your graphs would be good, would be not bad, probably would be not bad. But also it would be really good to know whose are the friends, because it might happen, okay, so what can happen is that this Robert here, all of his friends are non-Hungarians. If all of their friends are non-Hungarians, then probably this Robert here is not speaking Hungarian. But if some of their friends are not only called Robert, because this is not necessarily their friends, but also having the language setting of Hungarian, then he probably speaks Hungarian. So this is the way how you can utilize different creation of graphs. I'm just going to close it, and I'm going to go back to the second stream, to the second part, and I'm going to see what do I have in the other database. So the other database, I have this vertex A connected to vertex B, and I have IDs. These are Facebook IDs. So basically, it gives me a list which profile is connected with which profile. So what I'm going to do is I'm again going to go to the. Any questions? So what I'm going to do. Oh, error again. You crashed it? Hey. Yeah, no problem. Can you go back? Can you redo it? Okay, no problem. Just delete. Already happened. Delete the chart and put in a new one. Yeah, that is not a serious crash. It's not. It's really. The serious crash is if you crash all of our resources. That's also possible to be done. I think that's difficult, but still possible. Okay, so let's go to the second stream, to the second data, and I'm just going to, I already did it. I'm going to load it. So what I want to do is, these are the edges. This is the edge set. This is the vertex set. This is the edge set. I have to combine the two things. So to combine that, I go here to build graph, and I say that I want to use table as edges. And if you click on that, you see a hammer which has two sources and one output. So one of the sources is a project. So I'm going to use from this point the project. You can connect also from here, but don't do it, please. Not yet. Connect it from here. So this means that I'm using the bare vertex only set without any edges, and connect this as the edges. So this comes the table. I don't think it is possible to connect the other way around. So I think you cannot mix it. If you try to connect it to the table, no, you can. You can do it, but it would give you an error message. So don't do that. Connect the project to the project and the table to the table. Okay, and here you have to set three things. Yeah, following me? So the three things. First of all, you have to tell the software that which is going to be the ID from the vertex set, which is the unique ID for the vertex itself. And here it is going to be the Facebook ID. Now this key, this primary key, should match with the edge sets from and to keys. So here, vertex A is a subset of the Facebook IDs, and vertex B is the subset of Facebook IDs again. So this is the settings what you have to apply, and if you apply, of course you can do it the other way around, like you can do this. This is going to be no difference, but still I would recommend to do it like that. And if you're done with that, just press the green button and enjoy the super high speed. There are 3,500 edges in my Facebook graph. And now I also see that these edge attributes appeared, vertex A and vertex B. Well, it's not too interesting. Otherwise, our data is the same. But of course, I don't have the connections based on the first names. So let's go and also visualize this one. Now everybody can decide what kind of visualization they want to use. But I tell you something. If you visualize any points, because this is my ego network, I'm going to be among that points. And if you go a second distance from that point, you are going to visualize everyone because everyone is my friend. So if you randomly select me, you are going to visualize everyone, and then it is going to be a little bit painful for the processor. So let's not do that, but let's still do some nice visualization. Okay, this is for me what comes out randomly. And yeah, let's put there the gender as icons. Let's put there the location settings as colors. I think this is already pretty nice. And interestingly, what I told you before about the language settings, it seems that there is some homogeneity in these groups if you are thinking on the language settings. It's also nice that if you go and select just one, then yeah, then they're going to appear only with their own friends. And if you want to make it like a little bit bigger, then you can select randomly 3 guys. And the interesting thing is that I think we managed to select 1, 3 slightly different guys and girls. 1, so all of their friends here. 2, all of their friends here. 3, all of the friends here. This, for example, a quite interesting lady. All of their friends are also ladies. Sometimes, yeah. And I also would like to suggest you to use this 3D visualization. And you can again visualize all the graph. The way I'm going to visualize all the graph, I just pull it up to radius 2. It is going to visualize everything because a randomly selected person, radius 1, I am there. And from me, everybody is there. So radius 2, anyone is going to be the full graph already. So let's take a look at this graph. Would you think it is a small world graph? A small world graph. Just looking at this graph, do you think it's a small world? You remember what was the definition of the small world graph? Small characteristic length, large consolidation. What do you think?
Yes. Yeah.
Absolutely. This is the most beautiful example for a small world graph because everybody is either one distance or 2 distance from each other. Very small characteristic lengths, and you can see these nice clustering things. These are the clustering. These communities are those of my friends who are also friends of each other. And because this is Facebook, it is quite likely that one of these groups is maybe my family. One of these groups is my classmates from school. One of these groups are the friends who I play soccer with. One of the groups are the guys I met here in Singapore, the meetup group members. And of course, it is possible that some of my family members are also playing soccer with, or some of my school classmates are also colleagues today, and they are here in Singapore. So it is possible that you, as an entity, are a member of multiple communities. This property of graphs makes the thing super exciting, actually. This community and overlapping community cluster property will make that thing beautiful. Okay, now let's start. Yes.
While we are displaying this graph,
Yes.
we also show the labels like who is connecting in this network.
Yeah, so with the 3-dimensional visualization, you cannot do that. So if you are interested in the names, you have to go back to the 2-dimensional one. But before going back, I would recommend to take the radius to 1 to avoid to visualize too many points. And then on this chart, you can put there the names. And you will see how they are connected to each other. Okay, so do we remember what task do we have? Okay, first task, find me, alone. I didn't bring I should have brought chocolates. I cannot give any gifts next time. Next time I'm going to bring the first one who finds who I am in the graph is going to get a beer next week. And in the meantime, I can drink a Coke. Ooh, this is very hot. Are those cold? No. Cold? Cold or warm? Cold?
Yes, yeah.
Ah, okay. Relative. That is super warm. I think because of the... Yeah. Who I am. What's my first name? No.
Is this you?
Who? No, that's not me. Guys, this is my ego network. I cannot be a guy who is not connected to everyone on the chart, right? No, because he's not connected to all of these guys. I cannot be that. Do you think that I was so stupid to use my own name when asking this question? Of course I changed my name. The name is not Gábor. You can filter out the Gábors. Okay, guys, I help. So any kind of visualization you can do, even a visualization with just one point, which now in this case, the starting point is Tamás. You can see it because Tamás has a nice, beautiful Gloria, white Gloria here. That's why he is this point, this ID. Because this is one direction from him, I can show this too. Radius, if I take to radius 0, it is Tamás only. If I take it to radius 1, it is Tamás and his friends. So Tamás is here connected to everyone. I have to search for someone who is also connected to everyone, because that is going to be me, because this is my ego network. And that is going to be this guy here, called Benő. That's me. I'm connected to everyone. So if I go here and select radius 2, actually go and try it, doesn't matter, it will take some time, then everybody is going to be on the picture, because this is my ego network. Everybody is going to be there. I'm going to stop the animation, because that is using my resources. Okay, but we should have a more clever way to identify people. This looks like really not a professional way and not a very easily automatable way to find myself. So the easy way to find myself is to calculate everyone's degree. The degree is going to show how many friends I have. And because here it says that I have 403 members altogether. The person whose degree is 402, that is me. If there are 2 persons with 402, then that is probably me and a fake copy of myself. How to calculate degree? The easiest way to calculate degree is you just put here the compute degree or degree, and it is automatically going to find it for you. Or you can use the quite logical setup here. This would be a new vertex attribute. So the degree is a property of the vertex, right? Every vertex has its own degree, own number of friends. So here we are going to use compute. What was the name of it? Calculate degree. Where is degree? Ah, I'm wrong. It's not here. It's in the graph computation. Yeah, because degree is so important graph calculation. Like for example, the clustering coefficient. That it's here. So from the graph computation, I take compute degree. It's a beautiful snowflake, and I'm going to connect it with the project. If I go into the communication bar, it is going to ask me, okay, what should be the name of that variable? Yeah, degree, I like it. And then it offers me a lot of different opportunities. Like it can be incoming edges, outgoing edges, all edges, symmetric edges, in neighbors, out neighbors, all neighbors, symmetric neighbors. So it seems that under degree, it created me 2 different definitions. One is edge, and one is neighbor, and everything can be incoming, outgoing, all, or symmetric. Now, what does it mean, edge? Edge means that how many edges I have. But as I said, in Lynx kite, it can be like both directions. Then if I have an incoming edge and an outgoing edge, then that is basically 2 edges. If I have a loop into myself, that's already 1 edge. If I have multiple edges between 2 entities, then every time it's overlapping edges there, it's calculating as an edge. So edge and neighbor is a different definition. Neighbor would be the distinct number of friends who are connected with me through edges. In this case, in this Facebook case, because we don't have loops and we don't have multiple edges, it doesn't matter. Edges and neighbors are going to be exactly the same. The incoming and outcoming, that would be different, because as you saw earlier on the visualization, there are some directions there. Oh my, that was a mistake. Let's go back to radius 1. So you see that there is some direction here, like there are some different directions. The way how this direction is created is that from the smaller Facebook ID, we are linking to the higher Facebook ID. But it is like it doesn't make any difference. It could be the other way around, or I could have multiple edges here, symmetric edges, both directions. Basically, this is an undirected graph, but we are representing it still with arrows. This is because Lynx kite is working like that, unfortunately. So here for the degree, I would suggest to select all edges, but you would get exactly the same result if you selected all neighbors. It is going to result the same. And then let's click here, and then you will see that a new variable appeared here called the degree. And we can click on the histogram of the degree. I'm just going to get larger. Oh, where are you? And this is the degree distribution. So I can see that there are 300 friends whose degree is between 1 and 21. There are 91 friends whose degree are between 20 and 40, 40 and 60, blah, 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 blah. And I have one guy exactly one, I can zoom in, who has 402. That will be me. So if I want to see who is that, I can go to the visualization. Let's go to the visualization. Let's connect it. And I can say to the visualizer that, okay, I'm interested in Gábor, so I want to select one center, and I want to use custom restriction, add restriction, degree equals to 402. You don't have to put the equal, you will know that this is an equality. And of course, I should be a male, so you can add other restrictions, but you don't have to, you are going to still find me. So let's see. Hey. Hey. Oh yeah, and you have to go to pick. And yeah, oh, of course, and I'm not interested in the radius. And I want to see the first name, and it's me. Okay.
What's the degree again?
The degree was 402. That's just 1 minus all. Yeah. Yeah.
So what does it result? Sorry.
So you have to connect the visualization after the computation, otherwise you cannot refer on that.
No. What I'm asking
Yeah.
is vertex A, vertex B. What
Yes.
kind of data? What it means?
So both are Facebook IDs.
Both are Facebook
Yes.
randomly placed.
Not randomly, they are the friendships between my friends.
Okay.
That is the thing which was downloaded
It's
from
a
Facebook.
relationship. Okay, it's a
That is the relationship. Yeah, that is the relationship between them. Yeah. Yeah. Questions? Yes. The thing is that you press the next. That's okay because it's already calculated who is that. But then click out from here because now you're visualizing click out, and put the radius to 0 because you don't want to see everyone. You just want to see that one.
Okay, got it.
That's it. Okay. Let's find my wife. Before we are going to search for my wife, we are going to do another interesting data engineering stuff. We are going to filter out the outliers. Who are the outliers here? Me. Yes. I am the outlier because I have so high degree. I'm just making the whole picture wrong. Anyway, everybody knows that everybody is connected to me. So let's filter out me from the network. And let's see after that how the degree would look like. So let's close every window. And yeah, we can keep that visualization here. And let's use, for that we need filter. So let's see how we can do filter. Okay, so we are going to do a filter by attribute because we are going to use an attribute to filter out records. So I connected the filter, connected after computing the degree. And I'm going to filter out myself. So you can do it different ways. You can say that the first name is Benő, or even more likely to be able to filter out if you say that I'm not interested in that person whose degree is 402. So filtering it out, you have to use the exclamation mark. Exclamation mark 402.
Can you bigger or less?
or yeah, less than 400. That also works. Or even this works between 1 and 400. Even this would work. So there are a lot of different syntaxes what you can use here. I'm going to use the less than 400. You just click out, close the window, and that is going to work. And if you click the yeah, thank you very much. If you click the green circle, you are going to see it's calculating heavily. So what it does, it says that, okay, we lost one vertex. Now the new number of vertices is 402. And we lost 402 edges. So the new number of edges is 3098. All makes sense. This is exactly how it should look like.
So your wife's name is Alexandra.
That's a good guess.
Or
And
your
Alexandra
sister, your
is
sister.
very nice, but none of those are true. Unfortunately. But we are going to go exactly that way. So what you did probably was that you clicked on degree and said that, okay, so the next highest degree is 102. Let's zoom in. And there are a couple of highs. Actually, you can also use the logarithm. The logarithm is so nice. It is going to show you the logarithm distribution of that. And then you can say, okay, so it seems that now the extremes are those which are above, let's say, 40. How many of my friends are above 40? 13. So now if I'm visualizing all these 13 friends and I check the gender and I'm going to visualize maybe with the size, the degree, then my wife must be among them. So I'm going to do exactly that. I'm going to use a new visualization. And I'm going to say that, okay, so now I'm searching for, again, I have to press here. I'm searching for all the customers where the degree is higher than, what did I say, 40? 40. And of course, I'm just going to put the radius to 0. I don't want it to... Okay, and I want not one, but I want all of them. I think I have 13 or 12 or something, so I will put there count 20. So I'm going to have all of them. Yeah, I have all the 13. Let's put there the names, and let's put there the gender. I'm going to use color for the gender. And let's use size for the degree. So that's why you said Alexandra, because Alexandra has the highest degree, and she's a girl. And she's not my wife.
Your sister.
She's not even my sister. But let's see what we know here. What we know here. No, not very far from the truth. Alexandra is really nice, and I will tell the whole story later. But let's observe this chart. So what do we see? We see here on this chart all my friends who are having very high degree. And we see that Alexandra is connected to almost every one of them, but Sabina. The second largest would be Kinga, connected to Alexandra and many friends of Alexandra, but not to Sabina, not to Zsófia. And Sabina here, she looks really very alone. She only knows Gyuri, but none of the other high degree friends of mine. How is it possible that someone is in my network, has very high degree, but doesn't know all the other very high degree friends? The only way that it can happen, or the very possible way that it can happen, is that in my Facebook graph, which we saw earlier, there is one very large component, and Sandra and Kinga and Julia and Zsófia are part of that very large component. But there are a lot of other smaller components, and Sabina is collecting friends from multiple different components. The big difference between Sandra and Sabina is that it's very likely that Alexandra's clustering coefficient is really very strong. He knows everyone and all her friends knows everyone. But Sabina is not like the way that. And if you think a little bit that what is going to happen during your relationship with your wife, you are going to introduce it to all of your friends. But not all of the friends, but the friends who you are going to meet for different purposes. You introduce her to the family. Sometimes she is going to cheer you on your soccer game. Sometimes she's meeting the colleagues or the friends. So she's going to be part of multiple communities, but not too many people of the communities. While Alexandra might be there in the largest community, which is probably somewhere from the university, where you collect most of your friends, and she was very popular maybe at the university. So to get an answer for that, we should do a community search. We should find all the, so you remember earlier we saw these communities. Let's go back to that. This was the chart, I don't remember, but the beautiful three-dimensional chart. So let's try to identify all those segments, all those small topologies separately, and see that in which Alexandra is participating, and which Sabina and which the other girls are participating. So for that, we have to do a community search algorithm, and the community search algorithm is a segmentation algorithm. So here, from the segmentation builders, we are going to search for find Infocom communities algorithm. And I'm going to connect it here. And this is my communication panel, and if you click to find more, then it is going to tell the whole story of the community algorithm, how it is created, and I think it should even give you the article. Yeah, it gives also the article. It refers to the article how on that. So how the algorithm was implemented. This community search algorithm was implemented. Yeah, this is the article. Okay, that's not so interesting now. Let's see the settings. So, name for maximal click segmentation. Why do I need a name for maximal click segmentation? Because the way how the community algorithm works is it first searches for all the maximal clicks, and then from the maximal clicks it creates the community. So basically it is going to generate two type of segmentations, and for us the community is going to be the important. Now this must be set to false, because this one says that the edge required in clicks in both directions. In a telecommunication network, the both direction means that you call her, she calls you. It's a bidirectional. For creating telecommunication clicks and communities, it might be a very important structure or feature. Here in Facebook would be also important if we were not using an undirected version of the graph, but we are using, so this false means that basically it's true, but the data is not visualized that way, represented that way. We can give a minimum click size. We can keep it on default, 0 and 0.6. These are going to be different settings for the algorithms, but let's keep it on default. It is already going to give us, I think, a quite nice outcome. So when we click here, we already see that now we have two segmentations. As promised, we have a maximal click segmentation and a community segmentation. And if now you click on communities and you say open, it is going to create the community. So nothing happened. We are in a lazy mode. Spark is running the queries in a lazy mode. So only then it is going to be run when somebody is requesting some results from the RAM. But now we are requesting because we want to find out that how many empty segments are having and how many and how many. Now, okay, let's try to understand what is here. So remember, we had 402 profiles, friends in this network. From these 402 vertices, we have created 92 non-empty segments. We are having 92 communities from different sizes from 3 to anything. The total size of these 94 non-empty segments is 706. So it means that an average segment contains 7 members. But this must be so many customers or many people must be seen here multiple times, because I don't have 700 friends, I only have 400. So many of them are members of multiple communities, and that's why we call them overlapping communities, because the communities are overlapping to each other. That's why Sabina or Alexandra can participate in multiple communities. And we see that we cover 373 base vertices. So there are about 30 vertices which are not covered by this segmentation. So 30 vertices are not members of any communities. They are just like satellite friends of mine. Maybe they are my secret lovers. No, like 30 would be too much. So let's see the size distribution of them. So it says that in total I have 94 communities. The smallest communities are, the size of the small communities are between, actually let's do the logarithmic one because it's nicer. So I have 44 communities with exactly 3 members. I have 19 communities with exactly 4 members. I have 8 communities with exactly 5 members, and so on and so on. And you can see I have a very large community with 198 friends. And my second largest community is with about 30 friends, 30-something friends. So now I'm going to do again something which is a nice visualization. I'm going to use this visualization here. So I'm going to connect it with the new data, with the community search. And I'm going to say that, okay, I'm going to do here something really cool. I'm going to split the screen into 2 parts. And for that, I'm going to load the communities. So it's already created, it's cool. And I'm going to say that I'm going to visualize, I'm going to close this visualization. This part is closed. And I'm going to open this visualization. Oh, I see one segment out of the 93. But I want to see the largest segments. So do I remember the size distribution? Let's use the logarithm. Hey. Okay, so 30, 20. Okay, let's see everything which is above 10. Okay. Let's see if the size is above 10. Okay, I have 11 communities which are having more than 10 members. Actually, let's see what if I use the equal. Maybe I have even more. No, I have still 11. Doesn't matter. So let's visualize all of them. I click here to the center. I want to see all of the 11 ones. And here are all the big communities of my friends. So this is the very large one, and the next largest one was somewhere 30. Yeah, this is the next with 34, and all the others are 20 or less than 20. 23, 20 less than 20. And now I'm going to put back this visualization. And basically what happens is that the communities and the people are connected. So Alexandra is the member of the large community, but only one community from the largest communities. Julia is member of this large community. János, also member of this large community. Zsófia is member of this community. There are some who are also part of other communities. But if you take Sabina, Sabina is part of 3 large communities. And with this one, she is the winner. She is the winner of knowing most of the people from the large communities. So the answer would be it is Sabina who is my wife. Sabina is participating in most of the communities of myself. And although she doesn't have the top degree, she's behind. Alexandra, not much behind, but she's behind. She knows much, her knowledge about my friends, and that's why about myself, is way higher than Sabina's, Alexandra's, or anyone in that community. And of course, you are data engineers, so you would ask me that, okay, but again, I had to do segmentation and this and this and that. But if I have a huge database, I want to immediately select these pairs for everyone, not only for Gábor or Benő and Sabina, but also I want to find Alexandra's husband and want to find Zsolt's and Gábor's wife. So how can we do that? And then comes the article, this Facebook article. So there is an algorithm which automatically calculates this value and projects this value, what we calculated here, on the edges. So this is going to be an edge property, and it is called normalized dispersion. So for calculating the normalized dispersion, I need the graph where I'm still in, because I want my edges there. So I'm going to come here and say, okay, where is this dispersion algorithm? Dispersion, compute dispersion. After the degree, I can compute the dispersion. I'm going to change a little bit the graphics. And the good thing is that you don't have to tell anything to the machine. It is going to calculate dispersion with these automatic settings. It is creating this dispersion and normalized dispersion as the edge attribute. And then I'm going to ask to calculate. So remember, I'm still in the database because there are 402 vertices. And I can see that there is someone with 1.2 dispersion. So what do I have to do? I have to visualize myself and everyone whose dispersion is high enough. How am I going to do that? How am I going to do that? Okay, what I'm going to do is I'm going to use filter, and I'm going to select those ones whose dispersion is less than, let's say, 0.5. Maybe this is not a good idea, but let's do that. So I'm again going to use the filter by attributes. The good thing is that I can filter not only vertex attributes, but I can filter also on edge attributes. So I'm going to say that, okay, I want normalized dispersion to be larger than 0.5. Click here. Yes, it's calculating. I remained only 20 edges. Only 20 connections remained. Now, if I want to see all these 20 connections, I cannot visualize all the 403 customers. I should visualize only those where this dispersion is very large, where this dispersion is high. So what I'm going to use, I'm going to calculate again the degree, but this is the new degree, and then I'm going to do a filter on that. So I'm going to calculate again the degree. I'm going to give a different name. So this is the dispersion, high dispersion degree. High disp degree based on all neighbors. And then I'm going to use a filter. Everyone whose high dispersion degree is 0 is not interesting for me. So yeah, there are 382 friends of mine whose high dispersion degree is 0, so they are not connected with a high dispersion edge to anyone. I can filter them out. dispersion degree must be higher than 0. I have 20 edges and I have 21 friends and myself, 20 friends and myself, and that is going to be easy to visualize. So I want to see everyone. I want to see the names. I want to see, what do I want to see? I want to see the genders, because that would be important as color. And I want to see the normalized dispersion with width and with color. That is going to be a beautiful chart. Why don't I see everyone? And why Laszlo? Who is Laszlo? Okay, I lost the. I'm going to use this. Pick all.
The network science.
Yeah, it seems that everybody is my friend here. And the highest is Sabina. And yeah, basically that's it. That's what this algorithm find out, that she's the highest one. I was hoping that we are going to get a little bit more connections. So so it would be really interesting to see dispersion among not me and my friends, but with my friends and my friends. And to see that, we have to lower a little bit the threshold, but also have to again exclude me from the network, because like this is going to show everyone. Actually, we can do that. It's not a big. I think it's not a big deal. We just come here and say that okay, 0.5 is too high. Let's see 0.25. Yeah, it's a little bigger one. Can we see some connections which are not between me and my friends, but between friends and friends? No. Yeah, all connected only to me. So yeah, basically, if I want to go for more, if you want to analyze connections between my friends, then I have to filter out myself again. But okay, now we have an algorithm that we can automate, which identifies Sabina, who is the highest dispersion. It's very easy to find the highest one. And if we're going to go more, then we can say that, okay, so here, and we calculated dispersion, so the normalized dispersion. Let's go to the logarithm. Okay, almost everyone is 0. Oh, cool. So what we are going to do is we are going to say that we want all the calculated dispersions, and we are not interested in the high dispersion one, and we are not interested in me. So we are going to also, where is the degree? Also going to discard me. And that should work. Somehow. Oh yeah, I think I had one more mistake. Here, I think I should use the star. Yeah, there are no edges. Why? Edges. Why don't I have edges? 0 edges, oh my. Okay, I think I know what the problem is. because I'm still in the graph. And I should filter myself out from the graph. So I filter out myself, then the normalized dispersion should work, I hope. Yeah, now we have something. Of course, it's not too nice. Let's try to make it a little bit nicer. Let's use animations and let's use centralized layout. Oh, decentralized. Yeah, I'm trying to use different visualizations. Okay, Alexander has a lot of big ones. Let's see who still has big dispersions. Which is the most red? Chilla. These are really nice matches, but no. So all of these connections are very meaningful ones. I'm not going to go into one of these, but basically here we find the romantic relations or friendships or I mean strong friendships. Yeah, this is husband and wife. This is, yeah, these are Judith and Monica, very strong friends. I think also family. I don't find my favorite example, but I don't know. This is mother-in-law and the girl. So this is basically it. I think I will stop here, unless you are interested in the rest. Quickly, let me summarize. Where have I my slide? Okay. So why do we need this UI and this tool? Because working with graphs is super difficult. If you have these structures as tables and you want to use SQL, you would completely be lost. Probably you were completely lost like this as well, but if you have to go down with the scripts and the syntax with only tables, that would be very difficult. So what I think is that Lynx-Kite is a great tool the UI is a great tool to start to learn to work with graphs. But after that, you might not need the UI. You might only need some really good Python libraries. I'm not sure which version is here, but the newest version, yeah, this doesn't have, but the newest version has here a little button. You press it, and the whole thing is converted to Python code and the Python library. So the whole thing can be easily automated and still using the Power Apache Spark. I think we learned how to create graphs, and maybe if my next question is that can we do viral models, then it would be yes, we can identify who are speaking Hungarian, whose language setting is not Hungarian, because I can combine the name graph and the social graph, and those ones who have the same name and same friends, they are probably speaking Hungarian. The whole thing I can train it for the existing Hungarian speakers, so that should probably work. What are the basic descriptive analytics of the graphs? We learned that. We learned that there is the degree, there is the dispersion, there is the connectedness, the connected components. But there is still this question: why is big data? Why is graph a big data? So I think the answer for that is that you have a lot of big data type of problems, but you can solve them with small data resources. Every time when you are able to do sampling from a big data, and the sampling is going to create you a relatively good machine learning model, then you don't need really big data. It doesn't matter, and this is the same vice versa. So if you use non-big data methods on big data, like if you use logistic regression on big data, you are going to get exactly the same result if you are having the whole database or if you sample it for 1% or 2% of the data. You are going to have exactly, am I right? Yes, I hope. I'm going to have almost exactly the same values for the logistic regression. It doesn't matter if I'm training the data on, I'm training the algorithm on 1 billion lines or just 100,000 lines. The coefficients are going to be almost, of course, again, depends on a couple of things, but if there are not too many input variables, then it is going to be the same. So, can I sample graphs? That would be the question. Is it possible to sample graphs? And just you saw these connected components, and then everybody is appearing if they are a friend of me. So if you just go to second or third degree, it seems that it's not possible to efficiently sample graphs. If you do a random sample of Facebook, if you randomly select 100 profiles from Facebook, nobody is going to be friend of anyone of the randomly selected 100. So that is a bias. That is a strong bias. If you do ego sampling, that for the egos you are going to have high degrees, but the friends you're not going to have high degrees. If you say that, okay, let's start with egos and let's go not one step from the egos, but 2 step or 3 step. If you go more than 3 steps, you're probably going to have all the Facebook data because everybody is so close to each other. So the big data problem here with graphs is that you cannot really sample well. But if you cannot really sample well, you have to analyze the whole graph. But if you have to analyze the whole graph, and if your graph is big, then you need a scalable tool. And Lynx is a scalable tool. And the last thing is, can we use it for machine learning? Yes, because it was possible to teach the graph who is my romantic partner, who is my wife, and it would be possible to do a lot of other things. But is it possible to do supervised? Because this was not supervised learning, right? I was saying that these are the features which are possibly true for my wife, and I used rules and rules and rules and arrived to a conclusion. This is not a supervised learning. Is it possible to do supervised learning on graphs? And I think that is going to lead us to some next question, which is going to be answered on the next meetup. Any questions? Lost? Ladies first.
So my question is more towards the application side.
Yes.
So tonight you showed us how to make use of Facebook data, but then from what we just saw in the beginning, actually all the data are in like the CSV file,
Yes.
right? But you kept talking about like the graph. So I was wondering like whether this toolbox or this software package can be applied to unstructured data, for instance, like images or text.
It is possible, but how would you build a graph of an image?
It's possible, for instance, like for BigDataX, I know some scientists have developed some toolboxes in MATLAB, so we can calculate global efficiency, local efficiency, all the indexes relating to graph theory. So I wonder whether your package will also have that kind of future plan in mind.
So it is not programmed yet. Like for example, loading the image into this system, because the image is not going to be a nice CSV file, right? You have to do a lot of filtering and transformation with that file. But I don't think that ever going to be built in, because you can do all those things in other Python libraries. So first, create some semi-structured data from, or some usable data from your images. Like for example, let's run a convolution network on that, and instead of putting in the chart itself, let's put one layer's data as an input data, and then you can do. That's possible. Then you use it as a vector, and then your representation is going to be a convolutional network representation. Then the inputs are going to be that. And then, okay, then the question would be how you are, because these are going to be your vertices, right? This is a cat, this is a dog, this is a face, this is something. How would you connect them to each other based on what parameter. Maybe you have some data for the pictures, like this is from a film, this is from.
Yeah, for instance, like if I scan certain images across
Yeah.
different time points, then
Yeah.
I'll have the time series.
Yes, yeah. So yeah, it is possible. It can do it, but I don't see why it should do it. Why not you use different, like what is the benefit of treating images as graphs? And yeah, like if I think about Facebook, like Facebook has a lot of images, and Facebook can connect these images to the profiles, and the profiles are anyway connected, so Facebook can do it. Facebook can connect images to profiles and then connect based on that. Like this would be a bipartite graph. From a bipartite graph of images and profiles, you can build a homogeneous graph with only connecting pictures, and two pictures is connected if those are friends who uploaded those two pictures. Then you can do something with that. Then you can try to identify that those guys who are, let's imagine you have a picture with two persons. Those are the two profiles, or they are different ones. That can be a good question. That's possible to do. Actually, Facebook did a similar research. They were checking that, like, there are pictures with 1%, 2%, 3, 4, 5, 6, 7, 8, 9, 10, and then they were checking the genders. And it turned out that, yeah, if there is only one person on the picture, it's about 50-50. If there are two persons in the picture, it's about like 25-50, 25 or 30-30-30, whatever. It doesn't matter. But if there are more people in the picture, like say 7, 8, 9, 10, 12, 20, then the probability that all of them are boys is much higher than all of them are girls. Much, much, much higher. So the probabilities, the same gender pictures with boys are very much biased.
Because I was thinking that possibility, like some people, they just upload their photos to their Facebook
Yeah.
account, right? So then
Yeah.
Facebook can analyze it.
Yes, and they do, yeah. So that's possible. That would be also possible with our tool, but you need all those other libraries which are responsible for transforming your image data to something more structured. You can load text, and you can do text graphs. That's very meaningful. For example, we try to use PageRank on just articles, and the interesting is that what the PageRank gives you is more or less the content of the article. So you can do that. You can do those things. Yeah.
Oh yeah. So my question is that, like, I remember you told us that, like, in the latest version, like, Python code automatically generated, right? So how is it? So basically, it means like, so basically, so backend code is like, so which means like you don't use any like your proprietary like library to computing such a graph series.
Yep. Yeah, no. All of these algorithms, which are calculating the degree, the connected component, the clustering coefficient, the community algorithms, these are written in Scala,
okay.
and these are our own codes. I wouldn't say like proprietary, because all of the codes have their algorithm. So that's why it's linking that, okay, the community algorithm is using this algorithm. This is implemented in Scala under Spark. So like that's the way how it is implemented. And yes, I think so. That time when we developed the algorithm, Spark was also trying to build their own graph library called GraphX, and we did a very strong comparison that should we use GraphX for these algorithms, or should we use our own Scala algorithms? And it turned out that GraphX was not good enough. It was not scalable enough, so it failed on large queries. And that's why we built everything from scratch. But we still use Spark, but not the GraphX part. Any other questions? Yes?
I'm quite curious about how we could actually use this Benedek to have like link between like relations between like certain keywords.
So
Yeah.
is there any use case in that, or is there like some way to actually like create the interconnectedness between those components?
Yeah.
Like how like for example like solid component, which part of the system is it in? Like what is it linked to? That sort of information.
Yeah, so this text mining and knowledge graph building is a very interesting topic and a very widely researched topic. I'm really not an expert on it. So there are thousands of researchers or hundreds of thousands of researchers, and I did only a very few of these things. I think those guys who are doing real hardcore text analysis and text mining, they are really good analysts. So, but I can still tell a couple of examples what we did with Lynx guide. So one typical problem is to match people, match addresses, match names, match IDs, match things with each other. And then if the data is textual like address, then a matching is pretty difficult. Even if the matching is based on names, it's pretty difficult. Like, let's imagine that someone is called John Smith. With that name, you are probably going to match with a lot of people. So then you shouldn't use name as a match. But if your name is very unique at that environment is very unique, you might be able to use it. And this is simple graphs. This is very simple graphs. The other would be the address. So if the address is not as nice as in Singapore, that with the zip code, basically everything is coded in, but it's like something like in Hong Kong, where typically every street has at least 2 or 3 different names, one Chinese, one English, one old, one new, one low-rise, one high-rise, whatever. And they don't have zip codes, they don't have static zip codes, then creating a good database of addresses would be very difficult. And it's free text and it's very difficult. But what you see that, okay, an address is still a flow, a graph of vertices. Every vertex is part of the address, like the number, the road name, the type of, this is a road or a square or whatever. So then there would be a lot of vertices connected to each other. And depending on which position you are, what comes after what, how many times you are appearing in the database, because a street is going to appear a lot of times, but maybe a name of the condo would appear less times, obviously. So based on these things, these diggery things, it was possible to create a good algorithm to correct and match addresses. These use cases are something what you are looking for, or this is still too basic? Okay, that's different, yeah. Oh, this is already a knowledge map, this address tokenization. But yeah, the knowledge map. So yeah, so the other thing, it's very typical how they do it, like you have a big text, like an article or something, and you tokenize it first, and then what you do is every word is a vertex, and every time a word comes after another word, of course after tokenization, then this is connected. There is a connection. And that can help to build up some kind of a knowledge about the text. I think most of the AML algorithms are, the natural language and NPL algorithms are using similar techniques with graphs, that they're representing the information like that. And it's very easy with Lynx guide to do that, but then after what you are going to do, I don't really know. Yes?
So what's the largest data set that you try that Lynx can handle, like in terms of maybe gigabytes as well as the network size?
So gigabyte-wise or terabyte-wise, it is still not as big as video streams, obviously. But like vertex and edge size, the largest one was having 600 million vertices and I think 2 billion edges, something like that, 2 billion, 3 billion edges.
Did you manage to run the dispersion and all this?
We didn't do this visualization, the 3D visualization of the whole network. No. Yeah. But it's you can visualize really big ones, really big ones. By the way, if you're interested in how big graph these guys were visualizing, I think I have something on that. That was a very nice table. Yeah, so for example, that was a quite big one, but still not as big as what we analyzed with Lynx guide. So this actor network database contains 700,000 actors, and every 2 actors is connected with each other if they were playing in the same films. So there are about 30 million connections between them, which means that, yeah, one randomly selected actor is having about 80 other actors who they were playing together with in average. This is the famous Kevin Bacon graph. But this is still small to Lynx guide. So, yeah, you can put easily 2 zeros behind these numbers or 3 zeros, and we are going to be able to analyze it with powerful Hadoop cluster behind it, but still it would be possible.
So, is your company provide like a software as a service, or?
I never completely understand the technology, but how we are working typically is we are solving problems. So if the problem is identified and it is a graph problem, or if it's matching with us, we run a project, and then we can decide if it's needed to be automated, because the thing is that when you go there, you don't know, you still don't know that the accuracy is going to be good enough, the implementation is going to be necessary, so you're probably going to do a first run or a couple of runs, and then after you do the automation. And then we can just leave either this Lynx guide there and they can play with it, or we can be responsible for every month, fine-tune it and maintain it. There are separate engagements, different engagements with different companies.
Okay, so customer need to like prepare a Spark cluster by themselves?
Not necessarily. Like when we started 5 years ago, nobody had Hadoop clusters, so we were just going in with our 3 machines or 4 machines, and we connected them together and then prepared it. Today, one thing what they can do is just to use Amazon or Google Cloud or Azure. Or if they don't want, they have their internal one. So we just go and install.
You don't prepare those clusters for them?
Not really. Well, we can, and at the very beginning we were, so we had to learn all these things. But today, I think today most of the companies realize that there are very good players in that game, Cloudera, AWS, Google. Let them do the thing, and like for example Vodafone. Vodafone has decided 2 years ago to put everything on their own big data clusters, and they started to buy machines. And today they realize that it's not going to work, so they agreed that they are going to use cloud service. Yes?
So are there any interesting web analytic problems where the vertices belong to different types?
Yes.
For example, people and pets?
Yes.
House, cars?
Yes. This is a typical, okay, so the name of these graphs is these bipetrid or tripetrid or multipetrid graphs. We have experience, for example, devices like phones and phone numbers, because your SIM card can be put in many type of connection. One SIM card can put into many devices, but one device, you just put one SIM card, then another SIM card, then another SIM card. So it's a many connection. And you can learn a lot of things on that. Like, for example, you can identify these two SIM cards typically used in the same device. Maybe they are friends or maybe they are family members, sometimes switching the SIM cards using the same device. So it's a very cool topic. You can do a lot of things with bipetrid graphs with Lynx guide. You can do a lot of things. Maybe let me ask one question. So, how many of you are data scientists doing machine learning? You.
I am a data engineer.
All others are data engineers. No?
I'm a data engineer.
So who are data engineers? So who are you guys? I thought there are going to be data engineers and data scientists.
Developer.
They are software engineers. Who are software engineers? Okay, good. Okay.
Some people are just shy.
Who are shy?
The shy people wouldn't be that
Cool. Thank you very much, guys. I learned also a lot. So you were really great. I usually do this much longer, 6-7 hours. And you were doing very fast, and it's very late now. At the beginning, it was very warm, so even the dodecahedron was a complicated stuff. But you did great. Thank you very much. Yeah, if anyone is interested in the future in graphs, or in Lynx guide, or in Lynx, just reach me out. You will find me on the meetup. And yeah, like all the companies are hiring for data scientists, data engineers, software engineers. So yeah, I don't have to tell that.